Уважаемые коллеги, всех приветствую. У нас какая-то заминка с подключением председателя сессии, но пару минут пока ждем председателя. Пару минут ждем и начинаем работу.
Хорошо, меня слышно?
Александр, вас слышно.
Очень хорошо. Так, я правда не посмотрел, кто у нас. Так, сегодня.
Доклад вот выведен на экран.
Да, это первый, да, будет?
Да.
Сейчас я посмотрю, кто у нас докладчики. Так, просто у меня не подписано было. Значит, тут Казаков. Ну да, тут понятно. У нас Крафт. Хорошо, мы можем начинать, если у вас все готово. Извините за опоздание.
Начинаем.
Меня слышно?
Okay, dear participants, I'm really glad to say you hello on behalf of the organizing committee and begin today's session. Today we have 5 presentations, and the first one is presentation of Evgeny Kazakov. Evgeny, you are welcome.
Good morning. Good morning, dear colleagues. My name is Evgeny Kazakov, and my report is devoted to experiments on the study of complex structure materials destructed under high electron beam of Kalmar facility located in Kurchatov Institute in Moscow. Thanks a lot to organizers of conference for invited the report, which will allow to tell more details about the features of our setup and experiments we carried out. This slide shows the outline of my report. First, I'll tell a little about the history of this kind of research, motivation, and goals. Then I will briefly present the parameters of Kalmar installation and features of diagnostics. After that, I'll present the main section devoted to destruction of fiberglasses reinforced with nanotubes. Next, I will talk about other experiments carried out on our installations. At the end, I will briefly summarize and discuss the future plans. The active development of research in field of new structural material leads to creation new polymers and composite materials for the aviation and space industry. At the same time, even for well-studied polymers, a large difference is observed, like on this picture, in the destruction. The irradiation parameters for these two samples is very similar, but you see that the destruction is rather different. Also, you can see that PMMA organic glass has no broken area near the electron beam interaction place. When studying the strengths of properties, dielectric materials using electron beam, the question always about charge effect is very actual. I will present a result of study the destruction of fiberglasses reinforced with carbon nanotubes. In response to nanotubes, it was possible to achieve a difference in the conductivity of the samples by 3 orders in magnitude. It has also been repeatedly demonstrated that under powerful pulsed loading, the fraction of materials occurs quite differently than in the stationary cases, especially when the energy is released not on the surface but in the volume. This slide shows the results of irradiation of ignantine. Irradiation of ignantine I presented on the previous conference. Also, you can see here the irradiated spheroplastic samples. I will talk about them in the end. This slide shows the Calamari high current electron accelerator on which the experiments were carried out. It consists of a Arcadiev-Marx generator with discharges, a double forming line, and coaxial setup transformer located in the water volume. Explosive emission forms an electron beam in the vacuum diode, which irradiates the sample. The beam current reached 45 kiloamperes, the electron energy up to 350 kiloelectron volts. The device of accelerator allows changing the charge level of forming line. Therefore, the installation provides a very wide range of exposure structure. Let's talk a little about the Calamari diagnostic special features. First, the processes we are studying have characteristic times of order of 10 nanoseconds. Therefore, we use low inductive shunts and dividers to we use low inductive shunts and dividers, and one of the problems for high energy particles is measuring the interaction zone of beam target interaction. We use a massive LED pinhole camera with additional luminar 4 and additional film. We understand that the optimal thing will be using imaging plates with high level of linearity, but it's very expensive, and now we are thinking about optimization of this diagnostic. A high level of electromagnetic noises leads to use very bulk protection shields. Which parameters registered on Calamari installation? The current in vacuum diode, the input voltage, size of beam target interaction, Bremse-Starling power, plasma light dynamics, shadow and Schlieren imaging, of plasma and shock waves in transparent targets. Also, it's possible to estimate the mechanical recoil impulse. The registration, for shadow and Schlieren diagnostic, a laser based on yttrium orthoilluminate with neodymium operating at second harmonic is used. The pulse profile is shown on this figure. Smooth profile and long pulse duration allow us to consider the laser constant, since most of processes we investigate have characteristic time much shorter than the laser plateau. The registration of its own plasma or laser radiation is carried out using a Sphere 6 streak camera, which has a wide range of registration time. This makes it possible to study both plasma and shock wave processes. An important task is to synchronize the obtained images with the processes in the vacuum diode. This realized using the LED located at the edge of the camera's time analyzing slit. The LED is powered from the current shunt of the calamari. The optical scheme made it possible to place a screen in the focus of the objective for implementing the Schlieren registration method. The next slide shows a scheme of for recording the propagation of shock waves in transparent samples. Wave traveling over the sample leads to change in refraction index. As a result, the laser beam is deflected and the shadow is deflected, and a shadow appears on the image for a while. This slide shows fiberglass samples after irradiation. Top white without nanotubes, in the middle gray 0.05% nanotubes by mass, and bottom sample black 6% of nanotubes. This slide shows samples in which destruction occurs through the entire thickness. This is much more than even the average range of electrons in such materials. A light region is observed around through the whole of the sample. You see here, here, and in fact here. This is also identified the destruction of binder throughout the entire thickness of the sample. Calculation is made by Monte Carlo method using the X-ray code. You can see the reference for 4 shots from this series demonstrate that the bulk of the entire energy is absorbed at the depth much less than the average electron range. The slide shows the results of calculation of distribution absorbed dose and attenuation of electron beam current in the sample. This slide shows the micro photographies of gray sample after radiation after irradiation. Breakings and burnings of glass fibers is observed. The similar pattern is observed on black samples. Also, it was found that for focused and defocused beam, the behavior of the plasma is significantly different. It's worth noting that the typical polymer exhibits a different pattern of behavior. At the same time, the picture is similar for other multi-component composite materials. This primarily concerns a focused beam. For the focused beam, the behavior of plasma is the same for different samples. The next slide shows the summary table of the results of fiberglass reinforced with nanotube study. The table lists two boundary values for each sample when the through fraction was observed and when it was not observed at the maximum input energy. Taking into account that the experimental error was about 20%, we can say that there was no significant difference in the destruction, while the difference in conductivity was about 3 orders between white and black sample. In this case, the radiatory input energy to carried out mass corresponds well to the specific coefficient of sublimation for materials in absence of destruction, but at high energy it's much more, and it was concerned with the fact that part of the beam energy apparently spent to interaction with plasma flying from the sample, breaking the chemical bonds and radiation. Next, I want to tell you about other most interesting result obtained by our team. We carried out a study of destruction of spheroplastic under action of electron beam from calamari installation. In this case, samples was considered filled with ordinary spheres, ordinary silicon spheres, and spheres conversed with tungsten. Silicon organic foam and nitrile butadiene rubber were also used as a binder. The most interesting result is that the formation of nano whiskers or nano wears was observed in sample with a silicon organic binder at a distance of 1 or 2 millimeters behind the fraction zone. Nano whiskers are formation with nanometer diameters and nanometer thickness and a few micron in length. They were not found near crater rising under the action of electron beams. The estimation of parameters of the material in the region differs significantly from characteristic conditions for appearance of such structures. In addition, in the case of using silicon-free elastic binder nitrile butadiene rubber, this structure were not found. For that, the scattering of not completely destroyed microspheres and material fibers were settled on the cathode. Was observed. In the case of silicon organic binder, this effect wasn't observed. The first result was of these studies were already published, but something is we're going to publish, but there are a lot of questions in this field. Now I would like also demonstrate the most interesting results obtained using optical diagnostic of calamari. We have investigated the propagation of shock waves of shock waves generated by the action of electron beam on various transparent materials. This slide shows a comparison of shockwave propagation pattern for polystyrene and PMMA. It can be seen that not only the nature of destruction, but the propagation of the, you see it, this picture was on one of the first slides, but also the propagation of shock waves is different for these materials, though they are very similar in mechanical conditions. The next slide shows a comparison of passage shock wave to PMMA and K8 optical glass. The result is partly expected, but in the glass you can see spread outer shock, which was also observed in massive sample of polystyrene and PMMA. When we studied heavier glasses, we observed the propagation of two waves, which is well described in acoustic approximation: longitudinal and volume waves. This same effect is observed on PMMA with high defocused beam. The shock waves and acoustic approximation for many materials has been long studied and well described, but these experiments gave us the idea of looking for transit regimes. The first experiments in this direction has already been carried out, and I hope to present the results at the next conference. Now a bit about plasma dynamics. When studying the propagation of the plasma's own glow about 5 years ago, the interesting regime was obtained. At some point, the glow began to spread from the center to the periphery with very high velocities, about 100 kilometers per second. At the same point, we assumed that the pinching of the plasma cord occurs, but it was not confirmed. At the same time, this phenomenon was observed in both shadow and Schlieren photography. Moreover, the radiation was so bright that broken through the installed color filters. We are currently discussing possible reasons. The main version is appearance the plasma diode with the low density in which the additional breakdown occurs. So that's all I wanted to tell. The conclusions are presented on these slides, slide, the main conclusion is that the mechanism of destruction of materials with complex structure requires further careful experimental studies. Thank you for attention.
Okay, please answer the questions. We don't have so many questions.
The time of electron beam I see is about 100 nanosecond. Electron flux duration is 150 nanoseconds.
Diameter of the beam.
About the PMMI is destructed in another way than polystyrene, it's an interesting question. We haven't, there were a few ideas about the structure of these materials, but now our colleagues in theoretical department try to present a theory in 1D model, and I think we're discussing this model, and I think in half a year we can answer this question.
Well, I can translate the next question presented by Elena Polisadova. So she asks about the state of the material surface, for example, roughness. Does it have any effect on the result of the beam impact?
The roughness of material is not very clear, but I think that it's not very important. It's not very clear, but it's rather flat. We didn't polish the samples, but it was rather flat. It has good flats.
Okay, we thank the Evgeny Kazakov for his interesting presentation, and please, Evgeny Nefedtsov begins his. Evgeny, I hope you are somewhere here. Okay.
Good day for all Congress participants. My report is maths on cathodes after short pulse voltage impact on vacuum gaps. Sorry, where is that pointer? I have no instrument. Do you hear me? Yes. Do you hear me? Okay. The report will be built around the general topic study of the causes of vacuum breakdown. The properties of vacuum insulation have been studied for more than a century. Theoretically, vacuum insulation must hold electric fields up to strengths of several gigavolts per meter. I have no instruments to enter. Sorry. I have no user point. Sorry. Okay, I continue. However, theoretically, vacuum insulation must hold electric fields up to strengths of several gigavolts per meter, which correspond to the onset of intensive field emission from ideal cathode surface. However, actual electric strength of millimeter and centimeter vacuum gaps is 2 orders of magnitude lower than this field emission from ideal cathode surface. However, for today, there are various mechanisms which suggest for explanation of vacuum breakdown. This mechanism connects with the various small geometric or chemical inhomogeneities on electrode surface, such as metal microprotrusions and the electric microinclusions, which enhance electric field strength up to critical values. Oxide layers, which charged by ions, flows and come to breakdown state. Micron particles, which detach from one electrode with the same amount of charge, accelerate in the gap and strike opposite electrode, and other factors. As a result, high power density, which released on one of the electrodes, leads to sublimation of electrode material and discharge in the metal vapors. If one factor suppressed, another one captures the activity in vacuum breakdown initiation. Recently, it became clear that with the help of modern methods of surface cleaning, it's possible to exclude explicit inhomogeneities from the electrodes. Therefore, today, the search for factors of vacuum breakdown shifts to the atomic scales. Recent theories indicate that the initiators of vacuum breakdown may be defects of crystal structure of electrode material, most likely the dislocations. The main goal of this work is experimental confirmation of special role of dislocations in initiating the first spark on clean and smooth surface of cathode. Sorry. Some words about samples and experimental setup. Single crystal of copper plates, single crystal copper plates with sizes of 12 to 12 millimeter were used as the cathodes. For the first experiment, we use high voltage pulses of 200 kilovolts. The anode was a tungsten or tantalum rod with 8 millimeter in diameter. Experimental installation consists of three main parts: a vacuum chamber with the tunable vacuum gap, middle chamber filled by insulating gas and contains pulse forming elements, series resistor and adjustable spark gap, and also max generator. Here you see a voltage waveform without breakdown. This voltage and current waveforms correspond to full breakdown, which leads to heavy damage on electrodes surfaces. These waveforms correspond to vacuum breakdown interrupted on spark stage by arrestor, which leads to significantly less disruptions. This mode was our working mode. I cannot list my presentation. Sorry. Oh. In addition, we tried to reveal pre-spark morphological changes on the crystal surface under influence of short voltage pulse with a limited current. For this experiment, we used another installation with voltage pulses of 25 kilovolts. Here you see calculated voltage and current waveforms, taking into account the discharge capacity of vacuum gap at the beginning of spark. It can be seen that current action is limited only to only 1 nanosecond. Sorry, I have no pointer, so just a moment. I want sorry for delaying. My training examples was very well, but now I don't understand what happened. Sorry. Yes, 9th slide. This slide illustrates how we reveal outcrops of original dislocations on copper surface with the help of metallographic etching in the etchant of this content. Contours of etching dislocation pits have the form of rounded rectangles on 110 surface and triangles on 111 surface. After subsequent electrolytic polishing in phosphoric acid, copper surface and dislocation pits become a mirror smooth. And now results. After interrupted vacuum spark, we revealed three types of new objects. First, erosion centers that coincided exclusively with the outcrops of the original dislocations. Erosion centers in the form of strokes. And a few very small submicron erosion centers, and of course small solidified droplets. Despite the appearance of microscopic erosion centers, after action of vacuum spark, the samples generally look as clean and mirrored. However, immersion of samples into etchant for a few seconds leads to darkening of the surface under anode projection. Etching within a minute revealed contrast areas of thermal and plasma treatments around all erosion centers. In another cycle of experiments, we tried to identify a very first change on the cathode surface under low current treatment. On the mirror surface, such change can be detected directly only with the help of optical microscope in special mode of contrasting. The scanning electron microscope doesn't allow us to get acceptable contrast images of these objects. The new objects have the form of flowers or small elevations. Middle photo illustrates some activity of originally existing dislocation in such microplastic process. Our research shows that right before before the short pulse breakdown of the voltage gap, high-speed microplastic phenomena take place on the surface of electrodes. Obviously, this microplastic phenomena initiate under influence of mechanical tensile stress caused by electric field. In our case, the loading executes on the first atomic layer, which has specific mechanical properties and coincides with the zone of study. Microplastic process means a generation of new dislocations by surface sources of different kinds. Here I note some features of dislocation which are suitable for vacuum breakdown initiation factor. To save time, I pass this slide. And this, no, some words about dislocation energy. If we estimate dislocation energy per one atom distance according to this well-known formula, we get the value about 10 electron volts. This energy is sufficient to detach an ion or an electron from the surface of corresponding electrodes. Yes. 2 minutes. 2 minutes. This slide illustrates various mechanisms which lead to breakdown, and in conclusion, I not only experimentally established facts without any speculations. There is a preliminary pre-spark stage of vacuum breakdown associated with the plastic phenomena in near surface layer of the cathode material. And the second, the special distribution of spreading of the explosion emission centers at the beginning of breakdown development in millimeter vacuum gaps, appreciably determined by position of the dislocation outcrops on the cathode surface. Thank you for your attention, and sorry for technical technical problems.
Thank you very much for the presentation, and we have a couple of questions. Do you see them in chat? Okay, please answer them.
Известно ли начально... Вы предлагаете... Так,
ну, первый вопрос Владимира Ивановича Олешко про влияние объемной дислокации, и потом дальше несколько будет еще.
The first question is by Vladimir Ivanovich Oleshko about the effect of polymeric dislocations and micro-inhomogeneities present on the surface.
как делить при огне и микронеоднородности сущностных. Значит, я отвечу так.
Прошу
Значит,
прощения, только время для переводчика оставляйте, хорошо?
хорошо, я понял. Значит, объемные дислокации, возможно, влияют на интенсивность источников, то есть они могут быть как затравочные для появления новых дислокаций.
Well, volumetric dislocations can possibly have an effect on the intensity of sources.
Что касается микронеоднородности на поверхности, то мы, в общем-то, брали довольно совершенные структуры.
What concerns micro-inhomogeneities present on the surface, we have taken virtually perfect structures.
И видели только углубления на зеркальной поверхности, видели только углубления, связанные с дислокационными выходами, именно те, которые выходят на поверхность.
And we saw only the perturbations due to the dislocations outcrops that are on the surface.
Next.
The next one about the purpose, the aim, objective of the work. Was it to clean the surface or to damage, to destroy it? О цели работы здесь вот Александр Пушкарев спрашивает: очистить поверхность или разрушить ее?
Ага. Значит, наша цель, так, может быть, мне... We attempt to determine whether the position of first explosion emission centers and position of initial dislocation on the cathode surface are the same. And no more. Мы старались сделать наименьшие повреждения для того, чтобы определить, в каких местах инициируется вакуумный пробой на чистой поверхности, лишенной различных неоднородностей.
We tried to damage it minimally in order to find out the locations of the breakdown. The next question is about the problems with the tungsten anode frangibility. С хрупкостью, ломкостью анода из вольфрама.
It is not our problem. Это никак не имеет никакого значения. Мы использовали вольфрам или другие тугоплавкие металлы в качестве анода.
The use of tungsten doesn't make any difference in this case.
Только для того, чтобы они выдержали тепловую нагрузку от первых...
Just to withstand the thermal loading.
Мы не видели переноса вещества с анода на катод.
We didn't see the transfer of the substance from anode to cathode. Arsenij Kirikov asks whether you could use your setup to study thin copper films.
Yes, we study foil materials. Foil materials with thickness above 20 micrometers. but но тонкий, совершенно тонкий плен мы не исследуем.
So not thinner than 20 micrometers. Do you know the initial dislocation density of copper monocrystal?
Yes, of course, we know about initial density of dislocations because we reveal their outcrops by etching. It is on the all surface of sample contains about several tens of dislocational outcrops.
Okay, it seems that the questions are over. Thank you.
Thank you.
Okay. I suggest participants to thank Evgeny Nefedov for his presentation. And our next talk is presented by Yaroslav. So, Yaroslav, you are welcome.
Здравствуйте, уважаемые присутствующие. Меня хорошо слышно?
Good afternoon, dear colleagues, dear participants. Can you hear me? Yeah, we can hear you.
Спасибо. Я представляю доклад по теме пиролиз бурового угля под воздействием лазерного излучения.
I'm presenting a report entitled Pyrolysis of Lignite under the Laser Radiation Exposure.
В настоящее время основным направлением использования угля является энергетическое.
So now the most common direction of using coal is the energetic one.
Существенным ограничением использования углей как топлива является негативное влияние продуктов его горения на окружающую среду.
Well, a sufficient restriction of using coal as a fuel is its negative impact, the negative impact of its combustible products on the environment.
Большое количество работ направлено на преобразование угля в чистое, жидкое либо газообразное топливо.
Many works are aimed at converting coal into pure gases or pure liquid fuel.
Одним из способов получения чистого топлива является пиролиз.
One of the ways to obtain pure fuel is by pyrolysis.
В качестве объекта исследования использовался тисульский бурый уголь.
The object of our research was tissue lignite.
Для установления влияния минеральной составляющей угля на процесс пиролиза была произведена деминерализация угля методом частотного разложения.
To establish the effect of the mineral constituents of this lignite, we analyzed its mineralization.
Теханализ угля до и после деминерализации представлен на слайде.
The technical analysis of lignite prior to and after demineralization is presented on the slide.
Уголь подвергался дроблению на щековой дробилке, после измельчался в шаровой мельнице.
Coal was atomized in the ball mill.
Далее просеивался через вибрационное сито с размером ячеек по микрон.
Then it was subjected to sieving.
И после прессовался в виде таблеток.
And afterward it was pressed in the form of tablets or pellets.
В качестве источника лазерного излучения использовался лазер на кристалле итриалюминиевого граната с неодимом.
As a source of laser radiation, we use the yttrium neodymium laser.
Функциональная схема установки приведена на слайде.
The functional diagram is presented on this slide.
Излучение лазера ослаблялось нейтральными светофильтрами, далее с помощью
The laser radiation was attenuated by neutral light filters.
и фокусировалось на образец.
And then it was focused on their sample.
Для регистрации выделяющихся газообразных продуктов использовался анализатор газов.
To register the released gaseous products, we used the gas analyzer.
Ионизация газов осуществлялась посредством электронного удара пучком с энергией 70 электрон-вольт.
Можно раздробить.
Простите, что?
Предложение раздробить можно?
Да, конечно. Ионизация осуществлялась электронным пучком, энергия электронного пучка 70 электрон-вольт.
So ionization was conducted by an electron beam, and the energy of the electron beam was сколько?
70 электрон-вольт.
70 electron volts.
Далее приведены основные характеристики используемого лазерного излучения.
Here we have the main characteristics of the used laser radiation.
Длина волны 1064 нанометра.
Wavelength is 1064 nanometers.
Длительность импульса 120 микросекунд.
Pulse duration 120 microseconds.
Частота среднего импульса 6 Гц.
The pulse repetition rate 6 Hz.
Исследование лазерной пиролиза проведено в диапазоне плотности энергии от 1,15 до 1,95 джоулей на сантиметр в квадрате.
So here you can see the range of the analysis of the pulse beam, of the pulse radiation.
Далее. В качестве примера приведены зависимости изменения концентрации продуктов пиролиза от времени воздействия лазерного излучения с плотностью энергии в импульсе 1,95 джоулей на сантиметр в квадрате.
Well, here in this figure you can see the dependence of their alterations in the concentration of pyrolysis products on their duration of the laser radiation exposure with a pulse repetition rate of 6 Hz and the energy density of a single pulse of 1.95 joule per square centimeter.
При лазерном пиролизе бурого угля в среде аргона обнаружены следующие продукты пиролиза H2.
Well, upon the laser pyrolysis of lignite, we found out the following products.
H2, CS4, H2O, CO и CO2.
Yeah, so they are shown just here in this graph.
Далее. Зависимость состава газовой смеси от плотности энергии излучения в момент времени 9,5 на 10 секунд приведена на слайде.
This slide illustrates the dependence of the composition of the gaseous mixture on their energy density of laser radiation at the time interval shown here, and the the pulse repetition rate of laser radiation is 6 Hz.
Сумма горючих компонентов смеси газообразных продуктов пиролиза при плотности энергии в импульсе равной 1,95 джоуль на сантиметр в квадрате достигает 93%.
Well, the sum of combustible constituents in a mixture of gaseous products of pyrolysis approaches 93%.
Далее, на слайде представлены данные по выходу горючих компонентов на...
Slide also shows the release, the outcrop of combustible products.
На единицу массы прореагировавшего образца.
Unit of a specimen.
С увеличением плотности энергии в импульсе
with an increase of the density of a pulse,
выход горючих компонентов линейно возрастает.
the output of combustible products rises linearly.
И при плотности энергии в импульсе равной 1,95 джоуль на сантиметр в квадрате достигает 1,3 на 10 сантиметр кубический на грамм.
And at the density of 1.95 joule per square centimeter, it reaches, сколько достигает?
1,3 на 10 сантиметр кубический на грамм.
1.3, sorry. 1.3 multiplied by 10 to the third power cubic centimeter per gram.
При увеличении плотности энергии также возрастает потеря массы образца от первоначального состояния.
With an increase in energy density, we can observe, что возрастает?
Потеря массы образца от первоначального
Mass
состояния.
loss. We can observe a mass loss, an increase in the mass loss of the specimen, the initial mass.
Линейный рост потери массы указывает на то, что в исследованном диапазоне плотности энергии
The linear growth in the mass loss of the specimen,
Эффект экранирования поверхности образца
the
продуктами
effect
пиролиза
of screening of
не
the
проявляется.
sample surface. Можно поменьше фразы делать.
Да, постараюсь, спасибо. Эффект экранирования поверхности образца не проявляется.
The screening effect of the specimen surface is not revealed.
Аналогичное исследование было проведено для деминерализованного угля.
A similar research has been conducted for demineralized lignite.
Как и для исходного угля, продуктами пиролиза являлись следующие продукты.
The following products have been used as, for example, for the previous research.
H2, CH4, H2O, CO и CO2.
And these products are presented in the graph.
Но сумма горючих компонентов смеси продуктов составила 65%.
But the sum of combustible products in the mixture approached 65%.
А выход горючих компонентов составил 1,3 на 10 сантиметров кубических на грамм.
And the outcrop of combustible products reached 1.3 multiplied by 10.
Итак, после деминерализации
After demineralization,
горючих компонентов
a sum of
снизилась
combustible product decreases
на 28%.
by 28%.
Выход горючих компонентов снизился в 4 раза.
The outcrop of combustible products decreased by 4 times.
А потеря массы от
The mass
первоначального
loss
состояния
from initial state
снизилась в 2 раза практически.
are decreased twice.
Таким образом, минеральная составляющая тисульского угля оказывает влияние на процесс пиролиза.
Thus, the mineral constituent of tissue lignite has a significant effect on the pyrolysis.
Но какой же состав этой минеральной составляющей?
But what is the composition of this mineral constituent?
На слайде представлен химсостав золы частиц углей.
The slide presents the chemical composition of the coal particle ash.
В литературе отмечается, что минеральная часть угля может оказывать влияние на реакционную способность органической массы угля.
На что?
На реакционную способность органической массы угля.
Okay, the literature shows that the mineral constituent of coal can have an effect on the еще раз.
Organic mass.
On the organic mass of.
Также отмечается, что соединение щелочных и щелочноизмерных металлов
It is also noted that the changes in the alkaline metals
являются катализаторами процесса газификации углеродных материалов.
are the catalysts of the processes of gasification of materials.
В этом отношении используемый уголь представляет интерес.
In this regard, the lignite that we have used is of interest.
Высокое содержание кальция.
So is of interest the high content of calcium oxide.
Если минеральная составляющая может оказывать такое влияние на пиролиз,
if the effect of the mineral constituent is so high,
то она также должна оказывать влияние на облучаемую поверхность образца.
It can also have an effect on the irradiated surface of the sample.
Выполнено исследование морфологии образцов с помощью сканирующего электронного микроскопа.
We have studied the morphology of the surface of the samples.
На слайде представлена микрофотография поверхности образца до воздействия.
The slide shows the microphotograph of the coal sample surface prior to laser radiation.
Далее приведены микрофотографии после облучения.
Here we can see the microphotographs after radiation.
Видно, что образуется столбчатая структура.
We can see the column structure being formed.
Диаметр единичных фрагментов достигает 100 микрон.
The diameter of single units reaches 100 micron.
Расстояние между столбчатыми фрагментами порядка 50 микрон.
The distance between the column fragments is about 50 micron.
И на вершинах фрагментов имеются сфероподобные образования
At the
размером,
top, we can observe the spherical formations with the
размером 10
size
микрон.
of 10 micron.
Мгм. Далее приведена эта же фотография в характеристическом рентгеновском излучении.
Now we can see the same photogram in the characteristic X-ray radiation.
Мгм. Сфероподобное образование – это оксидные соединения кремния и железа.
The spheral-like formations are the formations of ferrum oxide.
Сферическая форма указывает на то, что они за время облучения нагреваются до температуры плавления.
This spheric form indicates that they are heated upon the melting temperature, up to the melting temperature.
Мгм. Таким образом, температура поверхности образца может достигать более 2000 Кельвин.
Thus, the temperature on the surface of the specimen can reach 2000 Kelvin.
Аналогичное исследование было проведено для деминерализованного угля.
A similar research has been conducted for demineralized coal.
Видно, что после облучения наблюдается совершенно иной рельеф поверхности.
Наблюдается.
Иной рельеф поверхности.
So we can observe that after irradiation, we can observe the... Еще раз что?
Рельеф поверхности другой.
We can observe the other structure, the other relief of the surface.
Образование столбчатой структуры, как в случае с исходным углем, не происходит.
We cannot see the formation of the column structures as in the previous case,
Но образуется губчатая структура.
but we can see the foam structures.
И микрофотография деминерализованного образца угля после лазерного воздействия в рентгеновском характеристическом рентгеновском излучении.
So we can see a photograph of demineralized coal sample after laser pyrolysis in the characteristic X-ray radiation.
Поверхность образца угля содержит лишь органическую часть, минеральная отсутствует.
Well, there is only organic constituent on the surface of their sample. There is no mineral constituent,
Для деминерализованного угля.
which is quite justifiable.
И на основе полученных результатов предложена схема формирования столбчатой структуры.
On the basis of the obtained result, we suggest the diagram of the formation of our column structure.
При облучении образца
Upon irradiation of the sample,
минеральные включения, не проявляющие каталитическую активность,
the mineral inclusion that doesn't reveal any catalytical activity
подвергаются термическому воздействию
is subjected to thermal exposure, to
и
thermal
экранируют
impact,
ниже лежащий участок органической массы угля.
and has a screening effect on the на что?
Organic mass of coal.
On the organic mass of coal. Okay.
Далее, органическая часть угля,
Further,
не
the
экранированная,
organic part of coal,
которая находится в контакте с каталитически активными включениями,
which is in contact with the catalytically active inclusions,
подвергается лазерному воздействию,
is subjected to laser radiation, to laser impact.
происходит интенсивный пиролиз,
We have an intensive pyrolysis,
и образуются глубоко проникающие пустоты между экранированными столбиками.
and we have some kind of cavities, some kind of emptinesses between the screened columns, the screening columns.
Основные выводы не прозвучали по ходу доклада, я их повторять не буду.
The main conclusions have been presented throughout the report. I'm not going to repeat them.
Благодарю за внимание вас.
Thank you for attention.
Yaroslav, thanks for your presentation, and we have several questions. You may start with the question of Viktor Mikhailovich Lisitsyn on the differences in the chemical process of coal in one coal field. Can I see them in the chat?
Насколько могут различаться свойства угля в одном месторождении? Свойство угля может меняться на достаточно широких пределах, да, есть такая проблема.
Well,
И
these these parameters, call parameters, can vary quite widely.
Да, может несколько плавать. Минеральная составляющая может плавать результаты теханализа.
So we can say it about the mineral constituent or about some other constituents. So these properties can vary throughout a wide range.
Далее, как влияет марка и размер частиц угля на спектральные и амплитудные характеристики свечения лазерного факела?
How does the grade and size of a coal particle affect on the spectral and amplitude characteristics of the laser glow?
В данной работе эти исследования не проводились,
We haven't studied it within this work,
и, к сожалению, я ответить не могу.
and unfortunately, I cannot give an answer to this question.
Так, этот перевод. Изменяется ли состав горючих газов во времени после окончания действия лазерного импульса? Время облучения составляло 10 секунд. После этого...
The radiation time was... сколько?
10 секунд. 10 секунд.
10 to the fourth power second.
После этого образец оставляли в закрытой экспериментальной камере.
Further on, the specimen was held in the closed chamber.
Состав газов не изменялся.
Состав газов?
Не изменялся.
Well, the gas composition didn't change.
На каком основании вы считаете, что температура образца при лазерном воздействии достигает 2000 по Кельвину здесь?
What is the reason to say that the temperature of the sample upon laser radiation reaches 2000 degrees?
Мы полагаем, вытаскиваем эти результаты из снимков СЭМ. Видно, что...
that these results are valid based on their on the images.
Видно, что вот на поверхности образуются сфероподобные образования.
We can see that spheric formations are on the surface, are being formed on the surface.
После этого провели картирование.
After that, we had some cartation.
Да, и вот установили, что вот эти вот сфероподобные образования — это оксидное соединение кремния и железа.
And we found out that these formations are due to the ferrum oxide.
Как раз форма сфероподобная указывает на то, что они нагреваются до температуры плавления.
And this spheric shape indicates that they are heated up to melting temperature.
На основе этих результатов и полагаем, что температура может достигать более 2000 Кельвин.
Based on these results, we can assume that the temperature can reach these 2000 degrees.
Какие-либо вопросы я еще пропустил?
As far as I see, you've answered every question. Yaroslav, thank you for your interesting report. And now, next presentation will be done by Oleg. Please pay attention that it will be linked with microwave-induced processes, making contrast to the previous reports. Oleg, please start your presentation.
Good morning. Okay, thank you very much. I'm very glad and happy to hear you in the FRA conference. And our report is a microwave-induced self-organization of layer follicles during enhanced hydrolytic polymerization.
So
And good afternoon, colleagues. My name is Margaret Gradova, and let me present our report, since my co-author is not quite sure in his spoken English. Do you hear me well? Okay, so let me start. A large number of works has been published to date on microwave-assisted synthesis, which is a convenient, green, and efficient method to obtain functional nanoparticles for catalytic, sensing, and biomedical applications. Microwave treatment provides heating and the direct energy supply to the system, facilitates chemical reactions and reaction diffusion processes. However, most of the studies on microwave-assisted chemical synthesis of inorganic materials were focused on the particle size distribution, crystalline structure of the products, and their chemical and phase composition. However, little attention has been paid to self-organization of the colloidal system under microwave treatment. And most of the studies we know have not addressed morphology of the dissipative structures emerging in the course of Zolgel transitions in the colloidal systems. For this reason, in our report, we briefly discuss the multi-factor nature of self-organization processes and self-assembly of dissipative microstructures in lyophilic inorganic colloids during microwave-enhanced hydrolytic polymerization of ferric oxides and oxohydroxides. Which were irradiated in a thin layer of about 1-3 millimeters in a glass petri dish using a standard 2.45 gigahertz magnetron microwave source with a power varying from 200 to 800 watt. And the experiment duration was up from half a minute to several minutes. Yeah.
Second.
Here are the preliminary results we obtained. Microwave treatment of the saturated ferric chloride solutions at different power resulted in the emergence of different dissipative structures in the colloidal system, and the morphology of the resulting structures, as well as their chemical composition and degree of crystallinity, depended on the irradiation time, microwave power, and concentration of the initial ferric chloride solution. Under the pictures, you can see the conditions of the experiment. Self-organization of membranous structures in saturated ferric chloride solutions has also been observed due to microwave-induced dehydration and enhanced falling condensation of ferric oxides and oxohydroxides. As you can see from this slide, a gentle 1-minute microwave treatment of the colloidal precursor resulted in a variety of soft matter structure formation, while the longer exposure, up to 2 minutes, led to either amorphous or crystalline mineral patterns of a uniform morphology. Microwave-induced self-organization under high irradiation power of about 800 watts resulted in less diversity of the dissipative structure morphologies because of the too fast water evaporation preventing hydrolytic polycondensation and favoring simple crystallization of the mineral phases in the system. Here you can compare the pictures with the irradiation at higher microwave impact, and additionally to the optical images, you can see here Kirsch-Sobel image processing algorithm, which has been applied for visualization of the microstructure of the dissipative structures obtained in our systems. You can see their morphological diversity and that they are really complex structures. A possible physical mechanism of microwave-induced structure formation in colloidal precursor includes several steps. First of all, during microwave irradiation of the solution, scattering occurs due to the loss of the energy beam through ionic conductivity and dipole rotation, leading to the energy dissipation. The larger the scattering coefficient of the precursor, the lower the microwave penetration, and the losses are associated with the movement of ions and depend on the ion size, charge, and electrical conductivity, as well as on the ion's interaction with the solvent molecules. Ionic conductivity of the solution depends on the concentration of the ions and also the temperature, while an increase in the ion concentration leads to in the scattering coefficient. Since ionic conductivity is due to the electrophoretic migration of ions in solution, When an electromagnetic field is applied, they move in the direction determined by the field parameters. In this case, the contribution of the electric and magnetic fields will be different depending on the magnetic susceptibility of the precursor, which suggests the contribution of magnetic to these effects observed. Secondly, since the movement of ions represents currents leading to the energy losses equal to the amount of heat released due to the resistance to the ion flow, a local heating of the medium arises depending on the ion composition of the flows emerging in the local region. Contribution of the certain ions is determined by their mobility, so there are prerequisites for heterogeneous medium composition at the local scale, determined by the difference in the chemical composition and the ion mobility. As a result, the ion concentrations in the local areas change, due to which a spatial disproportionation of the flows in different directions occurs, and the local increase in the ion concentration leads to increase in the scattering coefficients. The heating efficiency depends on the scattering coefficient, so microwave activated processes in the precursor of different thickness will proceed in different ways and result in the formation of different structures due to the differences in the energy absorbed, because heat and mass transfer occurs not only in the horizontal direction, and the half attenuation layer thickness is approximately inversely proportional to the square root of the microwave frequency. As the temperature increases in the sample, the dielectric losses occurring due to the contribution of the dipole rotation decrease, and the dielectric loss is determined by the ionic conductivity. Therefore, during irradiation, there is a transition from orientational ordering in the medium to the structure formation due to the ionic conductivity in the irradiated precursor, accompanied by the heat and mass transfer as a result of heating. Since the heating efficiency in the framework of the rotational mechanism depends on the characteristic relaxation time of the dielectric, which depends on its viscosity, a transition from the orientational ordering to a heterophase system is directly related to the induced phase transitions, resulting in self-organization of a complex of the coupled processes of ionic conductivity or ion transfer operating within a microheterogeneous colloidal system. Since microwave energy is absorbed during scattering by a dispersed precursor, according to the scattering coefficient at each point of the medium, different dissipative processes can be observed at different points of the precursor, depending on the local nature of the material and leading to self-assembly of various structures. In the case of formation of dynamic membranes and boundaries compartmentalizing the medium, the excess ion concentration on one side of the self-organizing membrane leads to the direct movement of ions under the microwave beam. Similar effect results from the formation of soft matter phases with a viscosity depending from the initial solution, since the sample viscosity affects the ability of a substance to absorb microwave energy and limits its mobility. In the presence of both conductive and dielectric phases, the gradient will be sufficiently high, since it is known that microwave penetration is considered infinite for materials transparent to microwave radiation and considered equal to 0 for reflecting ones, such as metals. Hence, a simple interpretation of the effect observed as a purely thermal effect of heating is unacceptable because of the selective mechanisms operating here depending on the chemical composition of the medium, which dynamically changes during microwave irradiation, and the phases that are different in composition, which become separated in space. Therefore, the response of different structures at each new time, each new period of time during their formation and metamorphism is different. So, for the small molecules and ions, the dielectric loss due to the contribution of the dipole rotation decreases with increasing temperature in accordance with the known laws of microwave electrochemistry, and for the large molecules and ions, this is ambiguous. Therefore, at the points with a different number of ions, self-organization can proceed differently. Thus, dissipation and self-organization are directly related to the processes that occur during microwave scattering. As a result of this, the presence of microwave-induced structure formation in a colloidal medium can be divided into conservative self-organization and non-conservative or dissipative self-assembly or self-organization associated with the scattering gradients and mass transfer determined by the structures different both in chemical composition and microwave susceptibility. From the chemical point of view, microwave-assisted hydrolysis of ferric chloride solutions produces polymeric iron oxyhydroxides and oxides, depending on the temperature in the system. This process begins from the partial dehydration of the hydrolysis products in saturated ferric chloride solutions, leading to the formation of Zol by means of polycondensation of ferric hydroxy complexes, producing oligomeric or polymeric oxyhydroxides. This is a so-called alylation process. And further cross-linking of the above precursor by oxo bridges results in the gelation of the colloidal system, which is known as the oxalation process. Some of the structures obtained in our experiments were shown to contain such mineral phases as acagenate, ferric hydride, goethite, hematite, lipidocrocite, magnemite, and some other mineral structures belonging to ferric oxyhydroxide, according to the X-ray phase analysis. So the main conclusions from our work you can see presented on the slide, and probably the most interesting conclusion is that we should study not only the resulting products of the microwave irradiation of colloidal system, but also it is very interesting to address their morphology and self-assembly processes during the synthesis, and probably the intermediate products which are formed during nanoparticle formation are the most interesting ones in this connection. So thank you for your kind attention.
Okay. I hope that we have several questions, at least one. Marco, please answer the question.
The first question is what's the depth of the microwave radiation? It's obvious from dozens micrometers to some millimeters in the layer.
Well, and the second question concerns the pH of the system. The pH of the system hasn't been maintained, especially in this experiment, because the ferric chloride solution itself possesses really acidic pH, and the process also included hydrogen chloride evaporation, which we really registered. And there was no buffer, and it was not the aim of our work to maintain pH. It was interesting for us to register the results of the native process of hydrolysis. Are there any questions?
My question. I typed two questions. First about pH and another on mass model.
Oh, now I see a new one. How microwave radiation affects on magnetic characteristics of the product.
It's really a good question because our products, some of our products are magnetic minerals, and consequently we can say that in different regions of interest, different products can be produced because the microwave beam can be different in the different positions of our sample.
Well, another question concerns the temperature of the medium. Actually, there was no opportunity to register the exact values of temperature during our experiment, but it really changes dramatically, and you see that the variety of morphology in the products results from the difference, from the temperature difference in the sample, the local difference, and we suppose that the local temperature was about several hundreds of Celsius degrees. And yeah, it really changes. At the beginning of the experiment, we can see that even the the hydrolysis process is not completed, and there is still some bound water in the system after probably several seconds of exposure. And when the microwave treatment is about 200 watt, and when we use more intensive irradiation or a more long experiment, it results in the complete dehydration. So heating of the system dramatically affects the results of the structure formation.
Okay, I suggest thank the talker, and it's interesting that about 10 years ago this conference dealt with most of all inorganic solids, and listening here here a report on normal wet chemistry, it's maybe a little bizarre here. Thank you once more.
Thank you.
And we all have the list the talk of Anton Zverev. Anton, you are welcome.
Hello, I hope you hear me well. Please tell something about that.
Yes, we can.
All right, okay. So I want to present our work. It's development in photochemical initiation, laser initiation of energetic materials. Laser initiation is far of a new idea, but several advantages encourage interest for this theme. It's electromagnetic pulses immunity, potential more compact or less weight initial system, and the main it's possibility to initiation the low sensitive energetic materials or high explosive directly by laser initiation without some sensitive initiation energetic materials. But this method has a fundamental problem. The most of energetic materials is transparent in visible and infrared area, where the most useful lasers work. The main question of all these 50 years of development is how to make interact laser initiation with energetic material effectively. For the pure energetic material, we can suppose only optical breakdown as a mechanism of laser initiation. So it's not very effective and requires a high power of laser sources. Usually, the most common way to increase sensitivity of energetic material to laser radiation is addition of some opaque particles, so opaque additives, or applying on the surface of energetic material thin films which can heating or exploding by laser radiation. All these methods has the final initiation stimuli in all these methods is heating or a shock wave from explosion of the additive. So when we use the less sensitive energetic materials for the stimuli, we get the less effectivity of these techniques of sensibilization. In our work, we try to find a way to sensitizing energetic material by photocatalytical additive, which can interact with energetic material directly with formation some metastable products and make initiation easier. I will tell about two methods which we find. One is addition of carbonyl contain aromatic substances, quinones, in example of phenantrenquinone and a PTN, pentyl tetranitrate, as the energetic material. The hydrogen abstraction is a driver of this mechanism. Quinone molecule in excited NP state can abstract hydrogen from PTN molecule and product radical can decomposed with the much less potential barrier than the initial PTN molecule. The second way is charge transfer, electron transfer from catalysts. We used metal oxides, magnesium, and zinc oxides. The main mechanism of this method, electron the driver of this method is photo-induced charge transfer from the catalyst to PTN molecule. Then the anion radical of PTN can decompose practically without any potential barrier, how is shown on the diagram. This method was approved in this work and practically, experimentally, and by DFT calculation. On this slide, you can see the scheme of experiment for the PTN phenantrenquinone composition. Both components was dissolved in acetone, then recrystallized in water, filtered, dried, and pressed as a tablet, thickness 1 millimeter and 3 millimeters in diameter. For investigation metal oxide PTN composites, metal oxide with addition of PTN mixing in a gauge mortar, then heated in oven with temperature slightly higher than PTN, slightly melting temperature. Then these samples used for optical test optical investigation by reflection spectroscopy, and this product, this oxide PTN interface, used as an additive to PTN. PTN was mixed by ultrasonic homogenizer in Gixane, and then dried and pressed the same sample as the PTN fentanquinone samples. In this slide, you can see absorption spectrum of PTN fentanquinone composite and the micro photograph of the sample. The little yellow crystals is fentanquinone. We can see the absorption band near the second harmonic of Yak-Nedim laser. It's 532 nanometers or 2.33 electron volts. So we can assume that second harmonic of Yak-Nedim laser can be used for initiation of this composite. In this slide, you can see reflectance spectrum of magnesium oxide and zinc oxide PTN composites and spectrum of pure components. In magnesium oxide, we found absorption band which we can't see in both pure components. Based on result of DFT calculation, we assume that this absorption band can associate with charge transfer between metal between magnesium oxide and PTN lowest unoccupied molecule orbital. In diagram, you can see the result of calculation for three different position of PTN molecule on absorbed on magnesium oxide surface. In spectrum of zinc oxide PTN composite, we don't see any new additional absorption band, but we can find some absorption win in turn into red area of the spectrum. Based on previous result of magnesium oxide, we can assume that PTN lowest unoccupied molecular orbital located lower than conduction band of zinc oxide, and the absorption can be associated with the same charge transfer from valence band of zinc oxide to PTN luma. So we can the third harmonic of Yakni-1 laser can initiate this used to initiation of this composite because the third harmonic the energy is higher than the band gap of zinc oxide, but it's well known that zinc oxide can effectively interact with second harmonic of Yakni-1 laser by two photon mechanisms. So we used the second harmonic for laser initiation of this composite. In this slide, you can see the scheme of initiation experiment. The criteria of the successful initiation are the intensive acoustic signal from the initiated sample and the explosion reaction entire the sample. On this slide you can see probability curves of pure PTN and PTN phenterol composite by second harmonic Yakni-1 laser. We can see the decreasing of the threshold fluence energy with addition of 0.2% of phenterol. And the curve become more sharp, so we can assume that we see the change mechanism. The mechanism changing. It's a stochastic initiation mechanism by breakdown hotspots in pure PTN and the initiation by additives of phenterol in the composite. In the slide, you can see the probability curves from PTN and oxide composites. The addition of magnesium oxide and zinc oxide doesn't affect on fundamental frequency initiation threshold. For magnesium oxide PTN composite, we see the decreasing of the threshold only on the third harmonic initiation. For zinc oxide, we found the decreasing of the threshold in 2 times on the third harmonic and a little lower threshold on the third harmonic. 2 times on the second harmonic of laser initiation. It's a green light, 532 meters. And if we use the optimal concentration of additive, it's 0.5 for third harmonic. We can decrease the threshold on 0.57, 570 millijoules per quarter square centimeter. I take back from motivation of this study. We show that metal oxide can use as a effective photocatalysts in laser initiation of energetic materials, and show two mechanisms. One of them is charge transfer from catalyst to direct to molecule of energetic material, and the second one is excitation of photocatalyst and then relaxation of electron to loom of energetic material. The main part of this mechanism that the lowest unoccupied orbital of energetic material must located in the band gap lower than conductive band of catalysts, and we can use standard techniques for synthesizing the photocatalyst for visible and near-infrared light using defects and impurities. It's mechanisms on this scheme number 3 and number 2. So use the modified some oxides and some more complex inorganic catalysts. We can try to find the way to initiate transport materials using near-infrared or visible lasers. Thank you for your attention.
Okay, Anton, thank you for your presentation, and we have at least 2 questions. I would like to answer them.
First question about value of delay. Wait a second. In this picture, you can see a real experimental oscillogram. The 4 microseconds, it's a delay of steel base where lie the sample. So typical delay, it's about 1 or really about 1 second or 1 microsecond or some more. About 1-2 microseconds. It depends what fluence we used. As we close for 100% probability of explosion, we get the lower delay of the explosion. Intervals. We use it's a question about intervals at the points on slide 8. Yes, this one. We use the we we use the square root from number of tests as a error or value for each test on each fluence, energy fluence.
Okay, as I see, we don't have additional questions. Anton, thank you for your report. And at that point, I think we may close the section. I'm really glad that we listened 5 really interesting reports. Thank the talkers and also thank our auditor. Thank who asked questions and discussed the presentations. I hope we will see in the next section, in the next sessions tomorrow and then. Thank you very much.